Welcome. Today we're going to be taking a look at the notes worksheet entitled Law of Sines Day 2. And so if you remember yesterday, what we did is we started exploring the law of sines, and we looked at two very definitive cases there where we could solve for the triangle. Angle, angle, side, and angle, side, angle. So if we have that information in a non-right triangle, we can use potentially the law of sines and a little other math as well to solve the other parts of the triangle. And so what we're going to do here is use the law of sines to look at a third case, and it is what is called side-side angle and ambiguous, certainly sort of the opposite of definitive. And so we'll kind of see what that means, of course, as we go through the process here. So what we're going to do is, well, first and foremost, we're going to need a ruler, a protractor, and a calculator. And please make sure you're in degree mode on that calculator. And I'm going to ask you to construct a couple oblique triangles here and just see what unfolds. So let's see if we can make some sense of this. So here's what I'm going to ask you to do. You're going to leave a lot of room above here, and if there's some overlap on your paper, that's perfectly fine. So what I'm going to ask you to do is just make a horizontal line segment, something like that would do. Just kind of get us going right there. And again, if there's a little overlap, that's fine. We can do some erasing or whatever. Shouldn't matter. Okay, now everyone, if you would, please put the protractor on that left end point right here. So put the protractor down there, and please mark off exactly 40 degrees. So again, mark off 40 degrees from the left end point. Okay, once you've marked off 40 degrees from the left end point, what you're going to do for me is now make an 8 centimeter, please go centimeters so this fits, 8 centimeter line segment through that mark. So again, 40 degrees, and now you're going to go 8 centimeters through that mark. Something like that probably. So once again, this is 40 degrees, and this, everybody, is going to be exactly 8 centimeters. If you can make that happen, obviously I'm just sort of freehanding mine up here. Yours is going to look quite a bit better, of course. Alrighty. Well, here's what I'm going to ask us to do. Grab your ruler, and from this endpoint right here to this initial side down here, I need you to rotate the ruler outward and find where it's exactly 7 centimeters. So you're going to stick your ruler here, starting here, and you're going to just somehow work it out so from here to here is exactly 7. Has to be. So you might want to move it outward a little bit here or inward a little bit, but it's probably going to be in this vicinity right in here. So again, you need to construct exactly a 7 centimeter second side, by the way, and have that in place. So 7 centimeters, please. Okay. And when you get an opportunity, if you're with me at this stage, put a little theta right in there. We won't talk about solving the whole triangle right now. All I want us to do is find out what theta is. And so as I'm hoping that you see at this stage, the scenario that you have at hand is what's called side-side angle, SSA. And so something that jumps out at me with this scenario is we have exactly what we were looking for yesterday. I have an angle and a side across from one another in a non-right triangle. And so I can begin to use that as what I called the constant ratio. And so I'm going to do exactly that piece, everybody. I'm going to go ahead and say that 7 matches up perfectly with the sine of 40 degrees. So that as a ratio should now be equal to 8 over, and now I'm going to get sine of theta. Okay. Now at this stage, here's what I'm going to ask us to do. We cross-multiplied yesterday. Obviously, this one is going to be a little different because I have a last step to take care of. If I'm going to find the missing piece, which is the angle here, I'm going to have to undo sine. And so I'm hoping you see this coming your way, but ultimately we're going to have to take an inverse on this. But for right now, here's what I need us to do. Take 8 times the sine of 40 degrees, and then let's divide by the 7. So remember on the cross multiplying, this times this divided by this should give us this piece right here. So what I'm looking for is sine of theta, let's get that in, is equal to something right in there. So I'm going to grab my calculator and do exactly that as well. So I have 8 times the sine of 40 degrees. I hit enter. Divide by 7. And I get that right there. I'm going to go to about 4 decimal places. And so at this stage, and I'm hoping you all see, I have about 0.346, something like that. So I cross-multiplied, and now there we have to go ahead and do an inverse, which is exactly what we're going to do. Undo sine, and we're going to get our theta right in here momentarily. So let's bring this up again, and I'm just going to do inverse sine of our answer, and I get about 47.27 degrees, give or take, somewhere in there. I'm going to go 47.3, make it a little easier for the second construction. All right, now, again, I did not draw this very well here, of course, because I had to do it freehand. You constructed it. If you don't mind, can you actually grab the protractor, if you would, and measure that angle and see? I mean, did our math correctly, so in all things considered, that should be 47.3 degrees right in here. That's the rotation, 47.3 degrees. Now, I'm hoping you saw that, because now we're going to see something a little different. And why this is not quite as definitive, that's the key word here, and it's more ambiguous than what we saw yesterday. All righty, everyone, so here we go. On this side of your paper, if you would, give me another horizontal line segment. Something like that would do. As you can see, sort of side by side right there. And same exact scenario, everyone. If you would, grab that protractor and please, from the left endpoint, mark off 40 degrees. And let's even do it again. 8 centimeters through that mark. So one more time. This part is absolutely identical. 8 centimeters there and 40 degrees right in there. Okay. Now here's what's going to be pretty fascinating. I'm going to ask you to do a 7 centimeter second side here, except instead of finding it from here to here, what you're going to do, everybody, is rotate it inward. Try coming this way, everyone, and see if you can match up. You're going to have to sort of tweak your ruler a little bit, and you're going to have to rotate it around. And what I need you to do is rotate it until you get exactly 7 centimeters from this top point right here to the initial side. It should be somewhere right in here, give or take, if you do your construction correctly. So I'm going to go ahead and draw in what basically would, the basic look of it. It wasn't perfect there, but something like that. So if this is 8 centimeters, now what you're going to do is rotate that ruler until it's exactly 7 centimeters at this mark right here and put that in. And of course, everybody, give me a theta right in there. And if you notice, what I just did is exactly what we did not see yesterday. I created 2 different triangles using the same 3 pieces of information. In this case, side-side angle, same exact side-side angle, but as you can see, an entirely different triangle as a result. So that's why this is not definitive. This is what's called ambiguous, not quite as clear-cut. But watch the math that unfolds here. So I'm hoping everyone is with me at this stage, and I'm still looking for theta. And so let's go for it. And what I see, everybody, is the 7 and the 40 degrees still match up. So 7 over sine of 40. And then as a result, wait a minute, the 8 still matches up with theta. It's still across from it in our non-right triangle here. I still get 8 over the sine of theta. And interesting, I get the exact same proportion as I did at the beginning. I would cross multiply and solve, and I would end up with the same thing right here. So sine of theta equals 0.7346. And I would inverse sine, and here, again, coming back to those pesky inverses, we see another limitation, of course. When I do an inverse sine at this stage, everybody, it's going to give me this, of course, right? Remember how inverse sine is defined. It can only give you an angle in between, theoretically, in degrees, negative 90 degrees to 90 degrees. Can it is it possible for an inverse sine to give us an obtuse angle, something that's bigger than 90 degrees? Absolutely not. So let's answer a couple questions with this, and then we'll figure out what that one is, by the way, in just a couple minutes. So I have a couple probing questions here to get us thinking about it. And it says, what type of angle do you get in degree mode when you take the inverse sine of a positive ratio? Exactly what we just saw in that investigation. When I do that inverse sine of 0.7 and change, the calculator is programmed to give us only an acute angle, something between 0 and 90 degrees. Here's the issue, though. How many angles are there between 0 and 180 degrees that produce that positive ratio? Hey, think about this for just a second, everyone. Here's the coordinate plane. Sine is positive up in quadrant 1, right? But sine is also positive up in quadrant 2. In quadrant 1, everyone, I get an acute angle, and that's what the calculator would give us, the acute angle. But here, everybody, sine is also positive, and I would be getting obtuse angles in quadrant 2. But the calculator can't get us that. That's the limitation. So I guess here's the idea. How many angles are there between 0 and 180 that produce positive ratios? There are two. One in the first quadrant and one in the second quadrant, going back to the beginning of the semester here. So one acute and one obtuse. One in the first quadrant and one in the second quadrant. And so the question, of course, is right here, guys. It's an obtuse angle. I made you construct it as obtuse. So the question is, how are we going to get it? So it says, how do we get the angle if it's obtuse? And do you remember kind of using that idea, not in the too distant past, where if I get what we would call the reference angle, how would I get the angle in quadrant 2? And if you remember correctly, when we are in radians, it was pi minus the reference angle. In degrees, everybody, that would be 180 minus the reference angle. And that would give us our angle in quadrant 2 if it's obtuse. So before we do our conclusion, let me go back one screen and let's go ahead and see. So when I do an inverse right here, it doesn't necessarily give us theta, it gives us theta prime. And so theta prime is going to be 47.3 degrees. It gives us that reference angle. And so as a result, of course, how do I go ahead and get what this angle should be? Well, we said should be 180 minus that. And there's only one way to find out. So let's go ahead and do 180 minus 47.3. And let's get that angle. And you guys are going to measure yours momentarily and see if it was on target. So about 132.7. And there we go. That's what this angle should be right in there. Hey, everyone, just for a moment, grab a protractor, if you would, and measure that angle. And you should see that the rotation should be 132.7 degrees. And so side-side angle, well, we're going to have to work around the math here a little bit. Theoretically, we could get two different triangles out of it. And you'll see a couple different situations emerge momentarily. But I wanted you to see that through your ruler and protractor construction. Okay, so let's fill in our conclusion, and then let's start doing some examples to move this forward. So unfortunately, again, SSA is what's called the ambiguous case. So in SSA, as a matter of fact, it could be two different triangles. Oops, sorry, let me quickly erase. It could be two different triangles, or one triangle, or no triangles at all. And we'll see all of this. We looked at the two triangle situation, but it could theoretically, with SSA, only have one triangle emerge, or with SSA, not even have a triangle be able to be built at all. So let me just go ahead and make sure I've got this, and then I'll just write this. Look at the information in the problem. Alrighty. So what I'm going to do is basically give you three examples, 1, 2, and 3, to match these three situations right here. So if you're asking yourself, wait a minute, how can we only get one? How can we get two? How can we get none at all? You will definitely see that come up momentarily. So let's go give it a try. So it says solve the SSA triangle or triangles. Again, I don't know. Determine the number of triangles as a result. So here's kind of the premise with this. It says angle A is 123 degrees, little a is 47, and little c is 23. And so you can do this a number of ways. It really doesn't matter. I'm seeing an obtuse angle, by the way, that 123 degrees. And so I can't do this definitively. I'm not going to break out rulers and protractors here, but I'm just going to draw a very rudimentary triangle up here. And I did see that this is obtuse, so this is 123 degrees. So I'm going to do that, which means little a across from it. This is the key. Little a and big A are across from one another. So here's my 123 degrees. Here's 47. And it doesn't matter where you put the other side, by the way. It's totally up to you. Not sure how we've kind of done this before. I think I had this as big angle C, so I'm going to do this one here as 23 as little c. It honestly makes no difference whatsoever. But with that said, I need that piece right there. And then let's see, I guess if we're going to solve, then this would make this big B and this would be little b. All right, so the question emerges here with this side-side angle as I rotate counterclockwise there. How does it work out? And there's only one way to work with this, and just do the math, work with the law of sines, and just see what the information and interpret what the information tells you. So let's do it. Everybody, I see the 47 and that sine of 123 matching up. There you go. There is your constant ratio, so to speak. And I am hoping, of course, that you see here that the 23 would match up with angle C. And so what we're going to try to do here is interpret what's going on with angle C. So the first order of business, guys, is to do a little cross multiplying. This times this divided by this. What I need you to do is get me to this point right here. So the sine of our angle, whatever it may be, is equal to something, some ratio. So the question is, what is that sine ratio? So everyone, I actually have this on my calculator. And so what I'm going to ask you to do is take this times this and then divide by this up here. Let's get to that stage where we have a decimal. And if you did it correctly, you get something right in here, which is great. So here's the interesting piece about this. And again, we've been sort of working and trying to deal with these inverses now for several weeks. Here is another situation where we're trying to do that. Basically, what I need to do is find angle C by undoing sine. The problem is I have this nice positive sine ratio over here. And as we know, there are angles, well, two different angles in our primary rotation that have a positive sine ratio, one in quadrant 1 and one in quadrant 2. So what you're going to write on your paper for me, just to get this moving along, is two angles where the sine of angle C equals 0.4104. Let me just make sure I have that number correct for you. One in quadrant 1 and one in quadrant 2. So I'm going to just write it as one acute and one obtuse. Okay, just trying to be as clear verbally with this as we go through, but let's see what we can do. Now everyone, if you would, it's time for you to take an inverse. So undo sine for me. I have it on my paper, so I'm not going to do it right here. You're going to do it on your calculator. Inverse sine of both sides. So inverse sine of 0.4104, and that would give us sort of our angle, our reference angle, as 24.23 degrees. That's what I get right there. Which means angle C can be 24.23 degrees, or, now remember, there's an obtuse angle that has that exact same sine ratio, and that would be in quadrant 2. So how do I get the quadrant 2 corresponding angle? I do 180 minus this. So I'm going to go ahead and do that right there, and it would be 155.77. Now guys, let's pause and breathe for a moment, and let's look at our triangle. If angle C, everybody, take a look at this piece. If angle C is 24.23 degrees, is everyone okay with the fact that now I have two angles and could probably find the third angle and go from there? Hopefully. The question I guess I have for you is it feasible in a triangle for this to be 155 and change if that is already 123 degrees? And if this is 155, it looks like we've already exceeded the 180 degree limit, and so this simply does not work. So even though this angle theoretically has that exact same sine ratio, it won't make another triangle. And so what I see, everybody, is the 24.23 degrees would work, but the other one would not. And so in this SSA, there's only one way to make the triangle. So that other one goes away, and we go with that right there. Alrighty. So guys, it's time to roll. So angle C is and can only be 24.23 degrees. So that goes right in here. And if you want to start drawing some things in, that's perfectly fine. But basically the 23 and the 24.23 degrees match up. Now everyone, what I think we need to do is just go ahead and put this together. As a matter of fact, well, I think I'll go over here, and now we go ahead and use law of sines to finish it up. Oh, actually, I'm sorry. Let's do this first. I have 123 degrees, and I do have the 24.23 degrees, and I think now we would get this to go to 180. So let's do that piece. So angle B, I'm going to do this completely for you, is just going to be 180 minus those two added together. So 123 plus, and what do we have, 24.23 degrees. So as I mentioned, this I do have on my paper here, so I'll go ahead and utilize that. And I have an angle B of about 32.77 degrees when all said and done. Okay, wonderful. So I have angle A solved for angle C, and it can only be one. Then I use those two to get angle B, and now everyone, I just need to use law of sines to get little b right over there. And so this is working out pretty well. I see this piece. So follow my lead if you would. 47 over the 123, and now this one's not too bad at all because I just have little b and sine of 32.77 degrees. This is on the easier end because we don't have to deal with any inverses. This times this divided by this. And if you don't mind grabbing a calculator there and doing exactly that, that would be great. And then we'll move on to the secondary example. So this times this divided by this. And I have on my paper about 30.33, somewhere in there. Okay, wow. Only one way this triangle worked, and as you can see, because just one more time on that, because that secondary angle that had the exact same sine ratio, so 155 has the sine ratio too, but it wouldn't make another triangle because I've already gone beyond 180 degrees. So I cross it out and onward. Okay, let's go ahead and do this one. Solve SSA, determine the number of triangles. Watch what happens here. And again, I try to be, I try to draw things to scale, but it's tough because you just don't know what the real look is. So I don't know, I'm just going to draw something like this, as rudimentary as it gets. And, I've got that 75 degrees. This is across from it is 51. And this is 71, something like that right in there. SSA. And now we have to deal with it, everybody. So hopefully everyone is cool with this piece, and I think really let's go ahead and see what angle B is all about. So let's go for it. I have what I'm looking for. I have a side across from the angle. So everyone set up your constant ratio there, sine of, 75 degrees. And then I end up getting, 71 over the sine of B, whatever it may be. Okay, perfect. Now, here's where I need you to get. Let's get this piece. What is the sine of angle B? Let's get to that stage, everyone, if you would. please get that calculator out again and do 71 times the sine of 75 degrees and then divide by that 51 right there. This times this divided by that. And if you do that, I get about, I usually don't round to 2 here, but I get about 1.34 give or take. And as a matter of fact, I'm just curious, maybe you see something about this piece already, but I am going to go ahead and bring up my calculator here and try to do an inverse, and let's interpret what the calculator is telling us. So I would do inverse sine of about 1.34. That's what I got when I did this. And of course, look what popped up, everybody. Can't do it. And this old news, but let's rehash it. Can I ever have a sine ratio above 1? No, absolutely not. So very simply here, doesn't work. Yeah, in this case, there is no way you can make this triangle. So this is kind of nice for our purposes. There are no triangles. It just doesn't play out. Theoretically, if I did kind of draw this out here, I'm just trying to see what it would look like, it might look something like this. If that's 71 and this is 51, it would probably bring you about right there. So there's 75, there's 71 units. If that's going to be 51, I don't reach, basically. And so I can't construct a triangle. Even though I have SSA here, there's no triangle. And again, the math bared it out, of course. Can't do this, can't make the triangle. So this is the situation at hand, of course, where there is only, well, there are no triangles. So I told you there was going to be one of each. So you kind of know, obviously, what's going on here. I'm just trying to give you a situation where we would see one triangle, where we would see no triangles at all from SSA, and here, of course, it's going to be the 2. But let's see why. So again, just kind of looking at this, just trying to draw a rudimentary triangle. There's 35 degrees. There's the 12 across. And looks like I've been doing a 16 down here. And let's get big B, big C, and little c. So I have what I'm looking for, everybody. That's why this is under law of sines, because it's a non-right triangle where I have the 12 across from the 35 degrees. So there's my ratio right there, everyone. And I'm hoping you see this, of course. The 16 matches up with angle B. All right, let's get to that stage. So everyone, if you would, 16 times the sine of 35 degrees and then divide by 12. So what is the sine of angle B equal to? And I actually don't have this one on my paper, so I'm going to go ahead and do the calculation. Just make sure you're with me on this. So 16 sine 35, and then let's divide by that 12, and so 0.7648, 7648 right there. Now, this is great. I am dealing with a triangle, though, and I'm trying to undo sine. And so here's the situation at hand is I'm trying to find the angle or angles that have a sine ratio of 0.7648. Well, everybody, there are 2. So one more time, just sort of our purposes, 2 angles where the sine of angle B equals 0.7648. One is acute in the first quadrant, the one the calculator is going to give us, and one obtuse in the second quadrant, which the calculator is unable to give us. So we have to at least acknowledge that there are a couple angles that could potentially work in a triangle having that sine ratio. So let's go ahead and get angle B here. And I get, when I undo this one I do have, when I inverse sine, everybody, I get 49.9 degrees. And so this right here, everybody, would be 49.9 degrees. And I would roll. But theoretically, I'm going to put a little or right here. See if I undid, well, if I did a 180 minus and find the obtuse angle with this particular sine ratio, it looks like I get 130.1 degrees. Now, I know that this could be 49.9 degrees right in here. I know it because these two would add to a certain number, and I'd have more to get to 180 in that third angle. the question, of course, is, can this angle also be 130 degrees, and would I have enough room to make another angle right here before getting to 180? Well, guys, if this is about 130, and that's 35, that takes us to about 165 degrees. So would I have enough to create a third angle? Absolutely. And so in this case, that can also fit in a triangle. Okay, so that's pretty much it. Now we would basically run the gamut here on both sides, just like we did last time around. So I'm going to set up just a couple things for you here and then ask you to kind of write in a few things, and then we'll go on to the next piece. So theoretically, you would make this 49.9 degrees, get angle C, and then little c. Also, because there are two different ways to make it, you would, in addition, make this 130.1 degrees, then find the third angle, and then use law of sines to get that. So I'm just going to go ahead and run a couple things that I have on my paper. And you're more than welcome to pause and just sort of do it on your own to make sure you're on target with it. But I have, if this is 49.9 degrees, then that third angle is 95.1 degrees. So that would work out nicely right there. The three angles now would be in place. If that's also 130.1 degrees, then I get enough room for an angle C, which is a small one, but it's still 14.9 degrees. Okay, and then everybody, what I would do, of course, is a little law of sines. Once I have the three angles, now I'm getting little c with that third angle. So the way I would personally do this is take our constant ratio, the 12 over the sine of 35.5, and set it equal to little c over the sine of 95.1. And I'll give you little c in just a second. But as I said, got to sort of take care of the other one as well. So sine of 35 degrees here, and then little c over the sine of 14.9. So just take a look at that piece. Make sure that makes pretty good sense to you. If you go ahead and cross multiply, and you do it for each, as I said, you get two different triangles there, both of which we can solve for. So in this case, I end up getting, about 20.8. And over here, I end up getting about 5.4. Okay. Please, if obviously I didn't go through each and every step here, so please pause the video if you need to and take a look at that on your own. But ultimately, two different ways to make the triangle, just like our construction. So in this case, two triangles. So I'm hoping you at least see how and why you either get one triangle and only one, or no triangle at all, or two triangles that can be constructed based on the information from SSA. Excellent. All right, guys, last piece. So we're going to do a couple area formulas here. And if you remember correctly, back in geometry, you probably just had the 1/2 base times height. And this is really just an extension of that, as a matter of fact. The 1/2 base times height really talks about it in terms of a right triangle. But in this case, we're going to sort of do this piece with an oblique triangle. So this works with side, angle, side. And I'm just going to give you the three scenarios. It's all the same formula. And it's 1/2 BC sine of angle A. And then let's see, 1/2 AB sine of angle C. Or just in the third one, again, it's all the same, guys. So you're going to write it 3 times, but it's basically the identical one. So AC and then sine of angle B. All right, so any one of the three. We'll go ahead and take a look at it. And as I mentioned, this is really just an extension of the 1/2 base times height. So let's do this one, and then I'll kind of show you that connection to the right triangle momentarily. But keep it nice and simple. We can avoid doing the ruler and protractor here. That's all right. Let's just sketch it out. I was going to have you sort of do the ruler protractor and really talk about how many square centimeters would be in it and so forth. But I think we'll look at that in a different way. So here's what I guess I would ask you. Let's go ahead and just do a line segment like this, kind of make that 8 centimeters. And then 135 degrees would look something like that and make that about 10 centimeters. So even though it's not going to be perfect, I think just based on the timing of today's lesson here, something like that. That's basically what I'm looking for. And so how many square centimeters? That's why I was going to have you construct it, so maybe we could take a good educated guess and then come up with our answer. But in essence, this is what side, angle, side is. Side, angle in between, and side right there. And as you can see, it just uses the sine ratio here. Keep it nice and simple. Once you have this, don't overthink this at all. It's just 1/2 times the two sides and times the sine of the angle measurement. Now we actually know exactly what sine of 135 degrees is, by the way, root 2 over 2. But that's all right. You don't have to worry about that. You can just let the calculator do most of the work. So if you don't mind, grab your calculator and just confirm what I'm going to give you momentarily. But 1/2 times 10 times 8 really times the sine of 135, which is root 2 over 2. And you end up getting about 28.3 square centimeters. Perfect. And that's it. It's a nice one. Very, very straightforward. And just if you don't mind bearing with me for one more sec here, you could see it really is just an extension of 1/2 base times height. So if I asked you something like this, I'm just making my numbers up now, what if that is still the 10 and an 8? What if that's 90 degrees right in there? Well, watch this, guys, just for a moment. Again, it doesn't relate to example 4, but I like just seeing connections here. So I would do 1/2 times the 10 times the 8 times the sine of 90 degrees. Hey, guys, what is the sine of 90 degrees? Well, sine of 90 degrees is just 1. So do you see you end up getting just 1/2 base times height? So I think I guess I said it in reverse form, but essentially the 1/2 base times height is an extension of this formula now up here. Just if it's a right triangle, it's just 1/2 base times height. Awesome. Cool. Well, I'm going to just sort of erase that. Well, no, I'll just leave it. It's fine. And let's go ahead and just box that up. That way we've got it. Alrighty. Well, some good stuff there, of course. Careful with SSA. Again, it's ambiguous as opposed to definitive. So, guys, if you have any questions at all, you'll just let me know. Try doing some of the problems that go with this, and definitely ask for help. Thanks.